Can you all hear me okay?
Yeah.
Okay, great. Okay, I see some chats. I guess they're not related to... They're related to something else. That's fine. Some reminders. Exam 4 is next Tuesday, chapters 29 through 31. What I might do is maybe have a session before the exam on Monday night and not have the office hours on Tuesday. I might switch them. Next homework is due on the 2nd. And notice I changed the date. It'll say a different date in Canvas. Okay. Motor Lab is due on the 30th. And my concern is from some questions that I've gotten like today, looks like some people have just started. I hope not. And I got to remember there's one more question I got to answer in the discussion board. I will answer it after class. And right now I'm currently grading the DC circuit analysis lab. One of the issues I've noticed, and I didn't think about, on the lab, on the larger multimeter, on the 20 volt scale, it says that the resolution is 10 millivolts. What does that mean? What does that mean? What's the resolution mean? Does anybody know? Yeah, it means that it's 0.0. It can measure the 0.01 volts, right? So resolution means that on this scale, it reads the 0.01 volts. And so when you were on that scale, were you able to read to an extra decimal place? You remember if you used a large multimeter? It actually gave you another decimal place. This is very confusing to me. I don't know why they write that. Yeah, Chase, I actually tested it. It actually measures the 0.001 even though it says this is the resolution. So that doesn't make sense to me. So I was a little bit more loose in terms of grading, what your uncertainties were on the voltages. Because it says 0.58 or it says something like 0.58% and then it tells you this resolution. I think it says 0.5%, and then it tells you how many digits, like the fifth digit. Okay, if it was the fives digit, then really the accuracy should be this. And a lot of people put down something to 3 decimal places, which is fine because this is really confusing. It was very contradictory, okay, in terms of describing the uncertainty in the measurements of the voltage. If the resolution is 10 millivolts and they say the error is to the 5 digits, that means that this number can vary by 0.05. Okay. So anyway, I had to kind of let things go in grading that part of the lab because the manual is weird in that aspect. Okay. It shouldn't be that way. I guess that's why they only cost like $30. Okay, just so you know. Yeah, it is. It was confusing. Okay. So yeah, I will. For most people, I wrote a comment. This is too low, but I didn't take off points. Okay, just because of the confusion associated with it. Now, if you use the other multimeter, the manual was more accurate to me. Okay, your uncertainties were actually probably made more sense if you use a small multimeter to measure the voltages. Okay, all right. So what I want to do today is finish the discussion on generators and talk about the displacement current. What I was going to do, and I was going to have you watch the video on displacement current, but I never captioned it. Although I did put it on, I did put it on one of our modules. So I do have a lecture on this, but I'm going to use it for the future because I never captioned it. So I'll talk about it today. We're actually at a pretty good pace right now, so I have time to talk about this. And then Thursday, I'm going to start chapter 32. Whatever I talk about Thursday will not be on the exam on Tuesday. Okay, let's be clear about that. Okay, because if you notice, it says chapters 29 through 31 here. Okay, so whatever I talk about on Thursday will be on the last exam of the semester. And it will be related to your lab too. Yes, I will. I should have time to do polls. So I have them set up because I didn't do them last time, but I have a bunch of polling questions I can ask you, and then you can we'll see how you answer them. Okay, which is usually fun. I wish I'd have more time to be able to do the polls. Okay, so I'll do that. Okay, so let's finish up talking about the generators. So, oh, I forgot one more thing. There was a question on Thursday, and I need to respond to it, and I didn't answer it well enough. We were talking about on Thursday we were talking about motional EMF. So we talked about the bar on the rails, and this goes to a question you asked, Ravtesh. And I wasn't very thorough in answering your question. Yeah, actually, you're right. I'm sorry, Kai. This is in chapter 30. This is 34.1.
Okay, cool. The displacement current stuff?
Yeah, this one in different textbooks and moves around all over the place. Okay. So yeah, it is 34.1. Okay. So let me go back to Ravtej's. She asked the following question on Thursday. So you have this rod moving to the right, and you have a magnetic field into the board. And of course, there's going to be an induced EMF in the circuit. There will be an induced current. And Ravtej asks, okay, well, that induced current produces a field. Does it affect the rod? So the way I interpret your question, Ravtej, was, does it affect the force on the rod? And the answer was no, but my answer was not complete, because this is what happens. If I push this rod, right, I give it some velocity. If I plotted the induced current as a function of time, let's say this is moving at a constant speed. You would think once it starts moving at that speed, let's say I give it a push at this time, the current's going to do this. And that's not what's going to happen. Okay, so I give it a push, and then all of a sudden the current jumps up. That doesn't happen. Because of the induced current, okay, and this goes back to your question, Ravtej, it does produce a counteracting field. And so what it does, it makes it harder for this current to reach its maximum value right away. And so what that current does is something like this. Okay, now how fast this goes up depends on the properties of this circuit. That's what we're going to learn in chapter 32. We're going to look at this effect in chapter 32. Most books ignore that effect. Okay, and typically because of the example we give you, that effect is small. So I'm hoping I was clear enough in responding to your question, Ravtej.
Yeah, it was because it seemed weird that it just bumped up and then it just went. So is it something similar to the concept of back EMF?
Yes, we're going to talk about a concept called self-induction. It has to do with the concept of self-induction and back EMF. In fact, I'm going to talk about that here when I continue my discussion. Although we don't talk about the inductance of the motor and things like that in this chapter, we will in the next chapter. So this is the first topic we will cover on Thursday. It's called inductance.
Okay. Mm-hmm.
When I did an example where I think I had a circuit here, and which had a switch and a battery that affected this circuit. Remember that example? It was a picture. I said you close the switch, this gets affected.
Mm-hmm.
There's an inductance here, but that's called mutual inductance. Because that talks about how one circuit affects the other. What we're looking at here is something called self-inductance. So I probably misunderstood your question in terms of, I thought you were looking into what the force, because we were talking about force at the time when you asked that question.
Mm-hmm.
So I was thinking, does it affect the force? But I didn't answer your question completely, because really what's happening is it affects how fast the current will build up.
Yeah.
Okay. If this was like a big coil or something, or if the circuit was just involved a big coil, and this takes a long time to build up, because you have a big inductance.
Yeah.
Okay. So generally it's ignored. The inductance, when we talk about it in chapter 31, we ignore that effect because the examples we use, the effect is small, or the effect, because it's small, this thing dies down fast. It's pretty fast. More like this.
Mm.
And we can vary the effect by varying the resistance of the circuit or the what's called the self-inductance. And again, we'll talk about that on Thursday. Okay? So I just wanted to clarify that.
Thank you.
Sure. Cool. Okay, so now let's look at the generator. And I think I showed you a simple example of a generator the other day. I had this little toy that I spun around and made the light go on, right? Basically, you're rotating a coil of wire in a magnetic field. And we said that when you rotate a coil of wire in a magnetic field, the induced EMF is described by this equation. Right, this came from taking the derivative of the equation for the flux. The end there is because the coil can have more than one turn. It can have many turns. And I think I showed you these little toys. And in fact, what I'm going to do, I'm going to change cameras so you can actually see some of these up close.
Professor, do you think you can define those terms real quick? So the capital N, that's the number of turns
Right.
on the wire, and then
A is the area of the coil, B is the magnetic field, and omega is the angular frequency at which you're turning. And I'll get to that in a minute.
Okay, and then is the omega t at the end, are those both inside the sign?
Yes.
Oh, okay.
Right. In fact, let me see if I have. I don't have the extra slide. Okay. Yeah, I'll go back because I'm going to do an example. But what I want to show you is, what happens when you rotate a coil of wire in a magnetic field. So and then connect my other camera. Just give me a second. I need my own camera person in here. All right. Okay, so what I want you to look at is this device is like a little toy. Let me move the camera back a little bit. Okay. So this little device, or if you can see it, this is the generator. So it looks like a little motor, but it's not. It's just a generator. This is just a generator, and I'm just going to hand crank it. Oh, I got to put the light. Sorry, I'm missing a light bulb. Hold on a second. Okay, here it is. And so as they crank it, the light bulb goes on. Does anybody ever have a generator on their bicycle? Nobody's ridden a bicycle with a generator on them? They've been around for a long time, so you have this little thing you push against your wheel, the wheels on the bicycle, and this thing spins, produces electricity, so that you can have your little light go on your bicycle. But no one's ever used a little generator on the bicycle? Okay. But there's interesting things about this. So if I take this bulb out, so my generator is now an open circuit because my generator is not connected to anything. When I spin this, it spins very easily. But when I put the bulb back in, I have a harder time. Why is that? Why is it I have a harder time spinning this? I have to actually apply more force to make this thing turn.
Is it because you have to go through the resistance of the bulb? You're fighting the resistance of the bulb?
Yeah, so what is that producing? I'm trying. You're correct in saying that. So the question is, what is that I'm fighting the resistance of the bulb. So I have a current, right? It's not really
Yes.
Is not backing me up. So I have a current in a loop of wire. If I have a loop of wire that has a current in the magnetic field, what is it going to experience?
An electric field?
Not an electric field. What makes your motor turn?
The force.
The force crossed with the distance crossed with the force. What's that called? It starts with a T. Torque. Yes, it's a torque. So what happens is when I run a current through here, a torque is produced because now I have a loop of wire with a current in it. If I take this bulb out, I have no current in my circuit, this open circuit. And so now there's no, when I rotate this, since there's no current, I can keep this going at a constant speed, no problem. Obviously, I have to overcome friction to keep it going at a constant speed. But once I've done that, it's going to go at a constant speed. It's going to be easy to spin. But once I put in a bulb, the bulb is using energy. It's taking energy from me. I have to put in more energy to make this turn at a constant speed. Does that make sense? And so that torque that's produced is called a counter torque. So imagine this is the power station. There's a bunch of people at the power station turning this thing to generate electricity. Okay? You all turn on your air conditioners. Guess what's going to happen to me when I'm turning this if you all turn on your air conditioners? This is going to be much harder to turn because you're using up all the energy I'm putting in. And you see that by the counter torque that's developed in this loop. Okay? In this loop here, the armature, which was the armature of the motor we used before, when I crank this, if I'm drawing current, if I hook it up to something, the more current I'm drawing, the harder this is going to be to turn. Because I'm developing a counter torque in this loop. Okay. So when everybody turns on their air conditioning, I need more people to crank this. Okay, I'm making a simple-minded analogy, but I'm going to need more people to crank this so this thing stays at a constant speed. Otherwise, everybody's lights go off. That kind of makes sense? And we can calculate the torque, at least for simple geometry. And I'm going to do that too. Okay. By the way, this is the motor that we used a few weeks back. I'm using it as a generator, so just so you can see it's running as a generator. Now granted, I can't spin this fast enough by hand to draw a large enough voltage. So you're not going to be impressed at all. I'm going to generate probably less than 2 volts. So I'm going to turn on the magnet. I have to have an electromagnet for this. Okay, so I turn on the magnet, and I'm going to crank the generator by hand, so you can watch the voltage that's generated. It's not very impressive, is it? In fact, this is actually generating DC current instead of AC current. Why is that? This is not generating AC current. This is generating DC current. Why am I saying that? That's not an easy question. It's a subtle thing. Remember, this is the motor I showed you a couple of weeks ago where I had the split ring commutator. This is generating the absolute value of that equation I showed you a little earlier. And it's really because of the split ring commutator. If I wanted to produce AC, then I'd have to have 2 separate electrodes for commutators. I would connect the brushes to these two like you see right here. Can you all see that? This is one brush to one conductor. This is another brush to another conductor. And now I'm going to get true AC current. Of course, you're not going to be able to see the variation on here because I'm turning slowly. But one thing you will see is it goes from positive to negative. Sorry for the problem with the reflection. It's hard to see it change sign, but it does change. It does change sign. So right now I'm running it as an AC. But when I take the commutator I use these two for the commutator, split ring commutator like you have for your motor. Now it's running as a DC generator. Okay. AC means the current changes direction. DC means it doesn't have to be constant, just in one direction. Okay. Questions on this? Okay. So let me plug in the microphone again. Oops, wrong one. Okay, so let me go to, so the, and I think I showed you this slide the other day. Once the load is connected, current flows, and the generator then develops the counter torque. The generator wants to slow down. The fact that the counter torque is developed is really a reflection of conservation of energy. And I just demonstrated the effect for you with the little generators. In fact, again, when we're on campus, I pass them around so you can see the difference. In fact, one of the things I can do with these generators, and I'll show this later, I'm going to actually take these generators, I'm going to take one of them and make the other one act like a motor. Just to show you that generators and motors are basically, they're basically backwards. Okay? A generator is a motor working backward. A motor is a generator working backwards. Okay? All right. So DC generators, they convert mechanical energy into electrical energy, and they need to keep the charge flowing in the same direction. So with a DC generator, you have to have the split ring commutator. So I've demonstrated this to you too. So let's just put in some numbers to give you an idea of what this means. Suppose we have, use some of my notes. Let's say we have a coil. So let's let N equals 80 turns. Let's let the area of the coil, I mean, it could be circular. The area of the coil could be circular. It could be rectangular, whatever. Let's let A equals 10 to the minus 3 cubic meters. Let's let the magnetic field be 0.8 Tesla. And let's let the frequency at which we turn, the frequency at which we crank the generator to be 60 hertz. So 60 times a second. Obviously, I can't do that by hand. Okay. And if you remember from physics 205, omega is 2 pi times the frequency. So omega is the rate at which the angle changes. Okay. In radians per second, the angular speed is going to be 2 pi times 60 comes out to 377 hertz. Okay, so now I've spelled out all the quantities. T is time, omega is the angular frequency or the angular speed, B is the magnetic field, A is the area, N is the number of turns. So if we put these values in, we'll get that the generator voltage is described by the following. The product of these three values comes out to, I'm sorry, not these three, these four, comes out to 24.1 volts times the sine of 377T. And so you have an AC generator, it produces this maximum voltage, and the voltage oscillates between plus 24.1 volts and minus 24.1 volts. Does that make sense? And if you let's say this is the open. This is, let's say, open circuit, meaning that it's not connected to anything. What if I connect it to it? Suppose I connect it to a resistor. Suppose I connect my generator to a resistor, whether it's a light bulb or whatever. And let R equals 1 ohm. Make life easy for us. Then my current is going to be huge, right? It's going to be delta V over 1. Why did I choose 60 hertz?
Isn't that just common on generators?
That's what we get in the US, right? AC current in the US is at 60. AC current is at 60 hertz. Okay, whatever comes out of your wall is 60 hertz. The thing that's different is this number. Okay, for most of our outlets, this number is 170. Now, when we get to chapter, and some of you folks might be saying, wait a minute, isn't it 120? Anybody, if anybody was thinking that it's 120, that's a different number. The 120 is a special way to average it, and I'll talk about that in chapter 30 and chapter 33. It's called a root mean square average. It's really the root mean square average of this function. But the peak voltage that's coming out of your outlet is 170 volts. And how would you determine that? How would you measure the peak average voltage? What tool would you use? Yeah, you would have to use an oscilloscope. You cannot use a multimeter. Because if you use a multimeter, the multimeter will give you 120. The scope, what's the scope going to do? The scope is going to give you a plot of voltage as a function of time. And when you measure this, you'll see that this is about 170. That's the amplitude. Okay. And then this cycle will take 1/60th of a second. All right? And so when we get to the next chapter, chapter 33, we'll be talking about AC currents and how capacitors and resistors and inductors affect an AC source.
Before you erase that,
sorry.
what? Oh, it's okay. I meant the other part, but why does the value in parentheses go from volts to amps at the bottom?
Well, this is current, and that's voltage.
Oh, okay.
Right?
So,
because remember what I said was, let's say we put a 1 ohm resistor in my circuit.
oh, okay. So if it wasn't 1 ohm, then it would be divided by, okay. I see.
Whatever the resistance was, right? All right, so let's say we have 1 ohm going through our circuit. Let's say we have a circular loop of wire rotating in a magnetic field that's carrying this current. How do I figure out the torque? How do I calculate the torque on this loop of wire? Torque is mu cross B. The magnitude of the torque then is mu B, the magnitude of the mu times the magnitude of the B times the angle between them. Well, mu is N A I. B is the magnetic field. It's some constant value in our example. And then the angle varies with time because it's spinning. But what's I? I is this. So the torque on that loop of wire is going to be I'll draw the T here. That would be the torque. That would be the magnitude of the torque as a function of time. So it's not a complicated problem if the magnetic field's constant. Are we okay with that?
That is 0.8 in the brackets, right?
This?
Yes.
0.8 Tesla, right?
Okay. Mhm.
Okay. And really that's it. That's all you need to do to calculate the torque. The more current. So the V generator is basically, yeah, you're right, Chase. That's just your EMF. You're rotating a loop of wire in a magnetic field. The picture you see on the screen is a picture for an AC motor. That's the only difference between the motor you're building and an AC motor. You have two slip rings for your commutator. The two are separated, in fact, in that particular case. So you can easily modify your motor into a AC motor if you wanted to. Now I want to say one more thing. Suppose you have a motor. Okay, so a generator, when it draws a current, develops a counter torque. A motor, when it starts spinning, you have a rotating loop of wire in the magnetic field, right? If you have a rotating loop of wire in a magnetic field, what's going to happen? It's going to generate a voltage. It's going to generate an EMF. It's called a back EMF. Which is actually a good thing. So when a motor starts spinning, the voltage across the leads of the motor is a maximum just when it starts to spin. As it spins faster and faster, the induced EMF gets larger up till it reaches its operating voltage. And so the total voltage across the motor will be whatever you apply to it minus the back EMF. And so when the current is operating at its maximum speed, the back EMF causes it to draw less current. In fact, motors want to be spinning at their operating speed so that they draw less current. And this effect is due to Faraday's law. Because in a motor, you do have a loop of wire rotating in a magnetic field. The flux is changing. So therefore, there must be an induced EMF in that motor. So if we denote the script E as the back EMF, if we say the back EMF, we call it this. Then if you have a motor that's running, the current in the motor, excuse me, is going to be the voltage you apply to it minus the back EMF divided by its resistance. What do you think when if you've ever used a drill and you're trying to drill something that's hard, you start pressing on the drill, why do you think it overheats?
The current?
Yeah, the current's much higher when it's spinning slowly. The motor's drawing a lot of current because this is small. And so the motor overheats. Whereas when you let it run at full speed, this is significant. So the example I'm going to show you I took out of a book. I think it's a little bit exaggerated, but here's my example. Suppose I have a motor that has a resistance of 4.1 ohms. It's a 120 volt motor. So at startup, when there is no back EMF, the current is going to be 120 volts divided by 4.1 ohms, which comes out to something like 29. Hold on a second. 29 amps. When the motor gets up to its maximum operating speed, the induced EMF, or the back EMF, is 118 volts. So now the current at operating speed is about half an amp. That's a huge difference. Of course, I think this problem is a little bit exaggerated. I took it from a textbook. I think I took it from a Physics 110 textbook, but this is kind of that's a big change, okay? From 29 amps to 0.5 amps. So the back EMF can really reduce the amount of current you're drawing. So you can actually, if you have a motor and you want to measure its current when you turn it on, you can just measure it and just see what happens.
And that's a 4.1 ohms on the bottom, right?
Yes, sorry. Thank you. Okay. So we talked about generators, torques, and counter torques. So what I want to do now is talk about a very important topic. We want to go back to Ampere's law. And this topic is either in textbook, is either in this chapter or it's in chapter 34. Just depends on the textbook you use. It also depends on the author. They move it around too, from one edition to the next. Anyway, I want to go back and look at Faraday's law. I'm sorry, not Faraday's law. Ampere's law. Let's write Ampere's law. Ampere's law is this, that if you integrate the magnetic field around a closed loop, and you can call this an S, ds, or dl, whatever you want to call it. This is true for any surface enclosed by the loop. Okay? That's true for any surface enclosed by the loop. And really this comes from Calc 3. However, there's a physical problem with this, and I'll show you what the issue is. Problem comes in when we have time-varying magnetic fields. Something's wrong with this when we're dealing with time-varying magnetic fields. This is okay if the current's constant. It's not okay if the current changes. And so the classic example is, suppose you have a capacitor. And you're charging it up. And let's say the current is, I'll use a different color. The current's going to the right. And instead of calling this I, I'm going to call it I sub C, and you'll see why in a minute. Or in a few minutes. Okay? I'm going to call it I. I'm going to call it the conduction current. The current due to the flow of electrons in the material. And what I'm interested in, by the way, let's put the charge on the plates. I'm interested in calculating the magnetic field at 2 points. I want to calculate the magnetic field here and over here. Same distance away from the wire. That's not a good picture. Okay. Let's assume these distances are the same from the center of the wire. This is point A, and this is point B. And we've done this problem before. It's very easy to calculate the magnetic field at point A, right? I just use Ampere's law. I know that the magnetic field is going to circulate this way around the loop, around the wire, and so I'm going to integrate in that same direction. The magnetic field is going to be the same anywhere around that loop, because if you rotate the loop, it's going to look the same no matter what. And so I'm going to get the integral of B dot S becomes B times 2 pi r, and that's equal to mu naught times I, the conduction current. And so B is mu naught I sub C over 2 pi r, whatever this distance is. Now, what about over here? What do I do over here? What do I do in this, in between the place of the capacitor?
There is no current there, right?
There is no current there. There's nothing penetrating that loop. So then what does Ampere's law say?
0.
It's 0. So Ampere's law says it's 0 over here. Okay? Ampere's law says it's the magnetic field is 0 here. Now, I can, if I wanted to, calculate the magnetic field here using BO sub R law. I mean, because charge is going like this on these plates and like this. Charge is doing this on this plate and like this on that plate. Okay? I can use the BO sub R law to calculate the field here, but I probably wouldn't know where to start because this is very complicated. And I know that the field is not 0 there. I can actually measure the field here, and I can, if I use a meter to measure the field here, I will find that it is the same value as almost, well, not exactly, but almost the same value as it is here. Because something's wrong here. Because Ampere's law says the field's 0 in here, and it's not, and it's not here. I know the field's not 0 here. I definitely know that. So that's an issue with Ampere's law. We need to figure out what's wrong with it, how to correct it. Okay? Questions so far? Okay, so let me advance the slide. Let's take a look . So, Chase, you have a question. Doesn't the current depend on how much the capacitor is charged? Yes. The current does, because once the capacitor is fully charged, the current goes to 0, right? But isn't it true that while it's charging, the current is time dependent? Okay, so we have a time, if we have a time dependent current, then we have a time dependent magnetic field. And we have a magnetic field here, but we don't have here. Now, when the current stops building, when this thing is fully charged, yeah, the field here and the field here will be 0. Okay. Let's look at it another way. Let's just draw a wire.
Professor,
Yeah.
does like as the capacitor gets charged, the charge on the plates is increasing, so like that increases the electric field, then the changing electric field produces the magnetic field, I guess.
Well, and then this was the solution that you're right. This is the solution that Maxwell came up with. Because once this is fully charged, once the electric field is maximized, the electric field is going to stop changing, right? But you're right. I mean, that it's the changing electric field, and this was his solution.
Yeah, I should have been in his place.
But yeah, that was the solution. But we want to look at the actual solution. I mean, the actual equation that he came up with. We want to look at that, and kind of briefly look at what his thought process was. Okay. But the other thing is this. Let's say we have just a wire carrying current, and then let's draw one of these loops. Like so. And I'm going to draw two surfaces. So the current's going to the right. Okay. I'm going to call the planar surface S1. And then the other surface, which would be maybe like the surface of a hat. Imagine you have a hat, right? The hat has two surfaces. One in the plane of the opening of the hat, and then the other one that's over the round part, the one that's over your head. We'll call that S2. Okay. This equation, it says that this is true for any surface enclosed by the loop. Now, remember that this can be written as the integral of the current density dot n dA. Now, there's an ambiguity in n on any surface because of the fact that over an open surface, n could be in either direction, but when you have a closed surface, that's not the case. So let's say we have this current going through this loop of wire, or not this loop, this Amperian loop. Let's say we can say this loop goes like this. The current through the flat loop can be written as the integral of j dot n1 dA. But this current also penetrates the second loop, where we can write the integral of j1 dot n2 dA. And generally these ends, if this forms a closed surface, are going to be in opposite directions. So the current going through this area and the current going through this area are the same. If you calculate the current going through the closed loop, the closed surface, you get 0 because it's saying whatever goes in comes out. Does that make sense? That whatever goes into the surface comes out. The flux going in equals the flux going out. Does that make sense?
Yeah.
Yeah, that part makes sense.
What if there's a source inside there?
Then wouldn't it be non-zero?
Yeah, but this doesn't account for that, right? This doesn't account for the fact that there could be a source inside here. If there's a source inside here, the integral over the closed surface is going to be non-zero. And whatever it is, whatever comes out is going to be dependent on whatever that source is. It's going to be directly related to what that source is doing. Isn't that what we have here? Look. Let's do this example.
Professor?
Yes.
But if we have like a source in there, wouldn't that be accounted for in the I enclosed?
Wouldn't that be what? I'm sorry?
Wouldn't that be accounted for in the I enclosed variable?
But it's got to go through both surfaces though.
Oh yeah, okay.
Sorry, what does J stand for again?
The current density.
Oh, okay.
Okay, so let's draw our capacitor again. Trying to make these plates thicker, I guess. And let's say we draw our surfaces like this. So we'll call this one S1 and this one S2. Now, how much current penetrates S2? How much penetrates this surface?
0.
0. There's no current that goes through that one. But what about through this one?
Whatever I is.
Yeah, so we'll call it I sub C. Okay. So you do have current penetrating through here. You don't have any current penetrating through here. That's because you have a source in here inside this thing. You have a charging capacitor. You can think of it as you're having a source or a sink of charge. In fact, in this case, it's a sink because nothing comes out of this source. I'm sorry, nothing comes out of this closed surface. Okay? And so again, sorry, this says that the second surface says that there's no field here, but the first surface says there is a field. So what did Maxwell do? Hold on, let me see if I can get my keyboard to work here. What did Maxwell do? Well, he thought that nature had to be symmetric. So if you look at Faraday's law looks like this. S or L, whatever you want to use. So he said that if a time-varying magnetic field can produce an electric field, then a time-varying electric field should be able to produce a magnetic field. And so he added a correction term to this. Now, where did that come from? Well, let's think about it. If I have a source in here, I need to have a term that represents charge coming out of this thing. Do you remember what integral you learned early in the semester involving the electric field that gave you a charge? In our second unit? Anybody remember? What about Gauss's law? Remember Gauss's law? Remember that? Mm-hmm. Okay. So he said, oh, maybe if I integrate the electric field around the surface, and then if I take the time derivative of this, that could be the correction to this. And so what he said was, he introduced this thing called the displacement current, I sub d, and said it was equal to epsilon naught times the time derivative of the electric flux. Look at the parallels between these two. Except for the constant, and look at the parallels between these two. And so now Ampere's law looks like this. It's called a displacement current, which is not a great name for it, but they call it the displacement current. Okay, so our displacement current is given by this expression. So I sub d is epsilon naught times d by dt of the integral of E dot n. And this is over an open surface. And so this is what was missing. You throw that in and then now everything works. Okay? So now that's what Ampere's law looks like. Ampere's law has this term in it, the displacement current. So time-varying electric field produces a magnetic field. A time-varying magnetic field produces an electric field. And this finishes off his four equations, right? There's one of Maxwell's equations. This is another one. And the ones involving Gauss's, oh, here's another one. And then the one for the magnetic field. Those are the four equations that pretty much describe all the fields in E and M. If you want to relate it to force, you add the Lorentz force, and then you're set. Okay? This was a huge breakthrough in physics. And Maxwell usually talks about, Einstein usually talks about the contributions of Maxwell's in this field. Okay, this was a big deal because it led to him working with these four equations to come up with the idea of electromagnetic waves. So let's look at the interpretation of this displacement current. Okay, so let's go back. Let's look at this example and let's consider, and I have the notation switched here. Let's call this S1 and this S2, and I want to calculate some things. Let's take a look at, let me redraw my picture. I got to redraw my picture, sorry. I want to make it like in the slide. I don't know why I changed everything around in the slide. What I want to do is look at S2. I want to calculate this for S2. In S2, this part is 0, but this part is not. So I want to calculate this integral for this surface. Okay. Now, what do you know about the field between two plates?
Uniform?
It's uniform. So the flux is integral of E dot n dA is just E times A. Right? And A is this, the area of this surface. Now, what's the electric field? What's the electric field between the plates? You remember? So then the electric flux is sigma over epsilon naught times A. What's sigma times A? Now let's take the time derivative of the flux. What's dq dt?
One.
Now you take I sub c over epsilon naught. So basically what you have then is the following. If I apply this equation directly, I get the same field here as I would, let's say if I calculated here at the same distance away. No difference. And the displacement current through S2 is equal to the conduction current through S1. And that guarantees continuity. That takes into account the fact that I have a source inside my surface. So I just calculated for you the magnetic field. So this next example, I pretty much did it. If this capacitor is fully charged, what's the displacement current?
Zero.
Zero, because dE dt is zero. dq dt is zero. Okay. And they've calculated the magnetic field for you already. What's the displacement current here? If I is this, then I sub d has to be the same. What's the time rate of change of the electric flux between the plates? Well, it's going to be the current divided by epsilon naught. If the current is 0.1 amps, sorry, I wrote that small. The value turns out to be where was my value? 11 times 10 to the 9th. Newton meter squared per coulomb squared. Or no, I'm sorry. Per coulomb second. Okay. So this was a big deal in terms of making all the equations in E&M consistent. In terms of you doing problems, there's not a lot of problems you do. You really, the main thing you need to understand is the significance of this. Most of the problems that you do are straightforward. Okay. All right, so I wanted to show you one more demo with the generator, and then I'm going to do some polling.
Professor, on the bottom board, is that mu sub naught?
Yes, it's mu naught.
Oh, okay.
Okay, I have my two little generators. And I'm going to try to do something interesting with them if it allows me. So I'm going to change cameras temporarily again. Then I'll do the polling questions. I have a bunch of them. So. All right. My goal is to connect one of these to the other. So this is going to be a little bit of patience. Just hold on a second. Okay, so what I have is a generator. I'm going to move this out of the way. I have a generator. Actually, I have two generators. So I have 1 and 2. So I'm going to use one as a generator and one as a motor. So I'm going to turn one. I think the bulb out. And hopefully the other one will turn. You guys see that? You guys see that? Okay, so I'm going to turn this one. That one should turn by itself. Unfortunately, I can't turn it fast enough because I need more than 2 hands. I'll try it again. Okay, I messed that one up. Sorry, hold on a second. These are not the best connections I have. I'll try it one more time. Hopefully you can see this bottom one turning. Oh, it's not working. You see it turning by itself? Just got this. Did you see it turning by itself? Okay. Okay. So anyway, so this just illustrates to you that the generator and the motor are basically the same. They're just one working in the opposite direction of the other one. Okay. All right. So let me disconnect this and let me give you a couple of polling questions. Let's see, let me switch. Sorry, it's very difficult to work with multiple cameras. No, not that one. Okay. And let me go back to Zoom. Okay, so please go ahead and answer the question on the screen. You see the polling question, right?
Yeah.
So go ahead. Now this one only has 3 choices, but some of the questions can have more than 3 choices, but I just made a generic poll. So let me know what you think what you can say about the induced current in this particular problem is. It's like about half the class has decided so far. Two-thirds have made up their mind. Two more people. I need 2 more answers, 2 more people to respond. I have 10 of 12 who've answered. I'm going to give you 10 seconds. 5 more seconds. All right, that's it. So I'm going to hit end poll. And I'm going to share the results. Do y'all see the results?
Yeah.
So I have a distribution of answers. So does anybody want to share why they chose their answer? Nobody wants to share their answer. Okay.
I chose C or 3 because in order for there to be like a force on any of the electrons, D and V would have to be perpendicular to each other.
Yeah, that's right. V would have to have a component perpendicular to B.
Yeah, not the whole thing. There has to be a component though.
Yeah, there is none. So yeah, the answer is C for this one. So that was the correct answer.
I was thinking, so like doesn't it produce like a compensating force in the opposite direction of B, but then when you do the right hand rule, then the current would have to be like vertical, I guess, if that makes any sense.
Yeah, but B and V are parallel to each other. The force is 0. Isn't that true? I mean, the cross product is 0. So there's no force on the charges that are moving in the circuit because of that. I mean, there might be some, some of them are going to be moving, have a component randomly in a different direction. But overall, really what happens is that the velocity of the rod is what produces that current. And so since the velocity of the rod is parallel to B, you're not doing any work on those charges.
Oh, so in our previous example, the magnetic field was like into the board or something?
That's right. That's
Okay.
why, those X's I drew inside the area, those represented a force that was into the board.
Okay, thanks.
All right, let's try another one. So let's try this one. So now we have a rectangular loop. It can move in any of the 3 directions given. In which direction can you move the rectangular loop so that it has an induced current in the loop? This one may be a little bit more challenging. So I got about a quarter of the class, or I'm sorry, a third of the class who's responded. We're halfway there. Three more people need to respond. Two more. Okay, last person. You want to respond? It is anonymous. All right, I'm going to hit end poll. So it looks like 11 people are responding. And so let me share the results. So most people chose B. And it's good. Only three, I mean, there was only three different choices. You guys only chose out of three of them instead of out of six. So in order for us to answer this question, what criteria do we have to use? We need to have a changing flux, right? I mean, that's one way to look at it. If the rectangular loop, although it looks like more like a square, moves to the right, is the flux changing through the loop? Yeah, it is, right? Because the magnetic field's changing. And in fact, if you want to think of it in terms of a V cross B, there is a V cross B there. It's not zero, right? What about for number two? Is the flux changing? Again, yeah, the flux is changing as you move away. The field is decreasing if you go in the direction of 2. And in fact, for number 2, if you want to look at it as in terms of QV cross B, there is a component of V perpendicular to the magnetic field that's going to cause the charges to move. Now, what about the third loop? Is the flux changing through the loop? No, it's not, right? The flux is not changing through the loop. There won't be any current. In fact, if you want to use V cross B, what you'll find is that you're going to have a V cross B in the bottom part of the rectangle and the same V cross B in the top part of the rectangle. And so even though you're going to have an EMF in the bottom part and the top part, there won't be any charge flowing because they're going to counteract each other. So the answer is B. The answer to this one is B. Okay. Let's do one like this first. So we have a conducting loop halfway into the magnetic field. Suppose the magnitude of the magnetic field begins to decrease rapidly in strength. What happens to the loop?
Is it increasing or decreasing? Because on the screen it says increasing.
Increasing, sorry. The magnetic field begins to increase rapidly in strength. This might take a little bit of thought. While you guys are answering, I'm going to try to draw a picture. Okay, where are we at? All right, got 9 people who responded. 3 more. Okay, actually, 2, I'm sorry. I think we're there already because the 12th person usually doesn't answer. Okay, I'm going to hit end poll. And let me share results. So we have a tie between C and D. So let me switch to the board. Just give me a second. So I drew a picture of this on the board. So B is increasing into the board. So the flux is increasing into the board. Lenz's law wants to oppose that change in flux, wants to produce a current out of the board, a magnetic field out of the board. Which way is the current in this loop?
Counterclockwise.
So it's like this, right here?
Yes.
Okay. So there's a current, so the current does this. So let's just take a look at this part right here. If we use the right-hand rule, we have B into the board, we have a current downward,
Is it counterclockwise because the right-hand rule would lead it into the board?
Yeah, so if I use the right-hand rule for the current, right, if I wrap my fingers around the wire, my thumb points in the direction of the current. My fingers will come out of the board towards us because that's what we want. We want the induced current to produce a magnetic field that comes towards us.
Oh, okay.
So that cross product is in which direction?
Right.
It's to the right? So the answer is D. Why do I not worry about these two?
They cancel.
They cancel. What about this one?
It is not in the field.
Okay, so I only have to worry about this one. Is everybody okay with that? These two cancel. The field's uniform, right? This one's not in the field. So really, this is the one that's going to... the net force is going to be due to this one. And so the force is to the right. So the answer is D. Does anybody want to do any more, or? Okay, I'll do, all right. It's helping, okay. So let's try this one. So in this case, the current through the top coil, hold on a second. The current through the top coil varies with time shown in that graph on the right. Which of the curves gives the correct current versus time in the secondary coil, the bottom one? The arrows also show the direction that's positive. I can give you a hint. You should be able to eliminate answers very quickly. You should be able to eliminate two of the answers very quickly. Okay, I got 9 people who've answered. One more. This is a little bit harder. Like I said, you can eliminate 2 answers very quickly. All right, I don't want to spend too much time. So, actually, one person left already. So, I think that's it. So, I'm going to stop here. I don't think the 11th person is going to answer. Let me share the results. You all see the results?
Yeah.
So let me stop sharing, or actually I'll leave it there. Why did I say you can eliminate 2 of the answers quickly? Anybody want to say guess as to why I said that? What concepts
Because
that
the
work
bottom
here?
2 are was the word like non-continuous?
Well, let's think about this. What principle is involved here? I mean, what chapter are we in? What is this chapter covering? Lenz's law and Faraday's law. What's Faraday's law again? Hold on. That one's hard to type in the chat. Isn't that correct? This is Faraday's law, right? In this particular case, what does the magnetic field do to? Or what does the changing magnetic field do to? It's due to the changing current, right? And what does the time derivative of the current look like? Let's plot di dt. What does it look like? Over the first range, what does it look like?
Just negative.
Like this?
And then 0.
And then the other one?
Positive.
So your induced voltage, of course, the induced current, is going to be proportional to this graph, right? So which answers did I just eliminate?
The bottom 2.
I just eliminated 1 and 2. Okay, because the derivative of the current, the derivative of a slope line is a horizontal line. The derivative of a horizontal line is 0. Okay, and so your choices are either number 3 or number 4. That's why I said you can eliminate choices right away. 1 and 2 are the ones you can eliminate instantly. Okay, because Faraday's law involves a time derivative of the current. It doesn't involve the current, but the time derivative of the current, because the magnetic field is proportional to the current.
Okay, but on the graph that you just did, you did the time derivative of the current versus time, and the question is asking just for the current versus time.
Yeah, the induced current, right?
Okay, I'm confused.
The problem asks for the induced current versus time, right?
No, it just says correct current versus time in the secondary circuit on the right.
So how do you get a current in the secondary circuit?
It's induced. I hear what you're saying. I'm just
Okay.
confused by it.
Okay. And that induced current is proportional to this. So, but still, what else do we have to do though? We have to apply Lenz's law, right?
So is the answer 4 then?
Well, let's check. I mean, it's either 3 or 4. How are we going to check whether it's 3 or 4? This is going to be really hard to draw.
By the slopes?
Well,
Is that
Because
current
if-
on the bottom loop created from the top one, or is that like already going through the loop?
I'm sorry, say that again.
Is that current on the bottom loop created from the top loop, or is that
Yeah,
already
that's the question. You know, how is the
okay.
current? What does the current in the bottom loop look like? Because the top loop is current is changing, right? Which means there's a magnetic field that's changing. And if the magnetic field is changing, the flux is changing. The changing magnetic field is proportional to di dt. I mean, anytime you have an electromagnet, anytime you have a current creating a magnetic field, the magnetic field is equal to the current times some geometrical factors. That's always the case. And so the time dependence really just depends on whether the current changes with time or not, right? I mean, that's really it. How is the di dt the same as I versus t? Okay, so let's say B, let's work through this. Let's say B is some constant k times I. Is that okay? Can I write is that okay for me to write the magnetic field that way? You might say, what's K? Mu naught, and then some geometrical factors. Is that okay, Kai? Let's pretend that, or let's assume that the magnetic field is uniform over the bottom loop. Okay, so what I want to do is calculate so that's going to give me the integral of K times B, or I'm sorry, K times I times dA. And let's assume that K times the geometrical factors are constant over the loop, just for simplicity. So then my flux the derivative of the flux that's my, and so, sorry. So this is my induced EMF, the magnitude of it. The current that's induced is d phi over dt divided by the resistance of the loop. And so that's going to give me these are all geometrical factors, and I'm saying is the induced current is proportional to the rate in which the current changes in the upper loop. Okay, is that okay, Kai? Because all I'm just saying is the magnetic field produced by the upper loop is current times geometrical factors, and we don't care about the geometrical factors really, unless we want to do an exact calculation. So now let's look at Lenz's law. Let's draw that top loop. Let's look at, I guess you got to look at the picture. Let's look at the top loop. The magnetic field points into the bottom loop, right? Is everyone okay with that? The magnetic field due to the top loop through the bottom loop points downward. Does that make sense?
Yeah.
And it's decreasing. Right?
Yes.
So in the bottom loop, you need to produce a magnetic field that's increasing. Downward, right?
Yes.
So if you look from the top, the current through the bottom loop is going to be counterclockwise.
Shouldn't it be clockwise?
Clockwise, I'm sorry. I got it backwards. It's in the same direction as the other one. The arrow points in the same direction, right?
Yes.
According to what the positive direction is for the bottom loop, if the current goes Clockwise, that's negative. So the answer is 3. Okay, the answer to that one is 3, not 4. Comments?
Can you show the board again?
Okay.
What was that written at the edge of the board, like on the silver lining?
Oh, let me. This should be erased. This is just delta V. Let me write it here. Let's see induced EMF.
Okay.
Okay. And my point was to say that the induced EMF is proportional to some geometric stuff and the current, or dIdt, sorry. Okay. This was a harder one. I'm going to do one more. Let me find one more. Maybe I don't have one more. I think I did all of them. This is the next chapter. I just for fun, we can try this one. This is from the previous chapter. Let's just try this one. This will be our last one, I guess. This is Ampere's law. Let me, yeah, I wish I could do more of these during the lecture. So let's try this one. It's an Ampere's law question. And you want the value of the integral around that loop. So that angle theta is the, just to be clear, is the angle between the normal to the loop and the current. All right, so I think I have pretty much everybody's response. There's always one person who doesn't respond. So I want to stop here and show you share the results. You all see the results?
Yep.
Okay, so let me go to this board. Let's write down Ampere's law. Ampere's law says that if we integrate the magnetic field around a closed loop, and you can use the L or S there, is equal to mu naught times I enclosed. Okay. What does this dot product represent?
Is it the component of the field in the direction of the loop?
So you're integrating you're integrating around the loop, right?
Mm-hmm.
You're not integrating perpendicular to the plane of the loop or anything, right?
Yes.
Okay, so this is around the loop. So do you need to know the angle between the direction of the current and the normal to the loop? In other words, do you need to know theta 1 and theta 2 in the figure? Right, these are within the plane, right? Yeah, you don't need to know theta 1 and theta 2, right? Because you're integrating around the loop. Theta 1 and theta 2 are perpendicular to the direction you're integrating. You don't need those angles. How many answers did I just eliminate?
Most of them.
Yeah, I got rid of 4 answers, right? So it's either E or F. Which one? How do I figure out E or F? The current's coming out like this. And the field essentially goes this way on both of them, correct? Essentially. Yeah, it's the one in which both are enclosed. So each one encloses the, that thing encloses both of them. Hold on a second, did I have that wrong? Yeah, it's the one which both are enclosed. Yeah, so for I2, isn't the direction of the field and the direction of the integration in the same direction? For I1, isn't the direction of the field and the direction of the integration in the opposite direction? So that introduces a minus sign, right, when you take the dot product. So shouldn't it be F? Okay. Okay. Yeah, you got to look at the direction of integration on both of them, because for loop one, the magnetic field is opposite direction of the opposite to the direction of your integration path. Okay. Yeah, these are there's a group at Ohio State that created a bunch of questions for all of physics, and these have been vetted with, and people have done research papers on them. These are the kind of questions that students have. You want me to send you some more? I mean, I do have I do have the conceptual questions online for this unit, and I have answers to those, so you can try those. And really, I wish I would have more time. I'd have to. I'm trying to figure out a way to include these questions in the class because I know the students like them, especially at the calculus base level. So if we had a recitation, this is what would I be doing in a recitation. I mean, a recitation where everybody had to take it, I guess. No, if you look under the unit for, they're in, which unit is it on? If you look at all the modules, I think it's in the first module. Hold on a second. I already forget where I put it. Let me find it real quick. I didn't want it to be obvious.
Yeah, I found it. It's in Unit 1.
Okay, it's in Unit 1. Okay. I don't have conceptual questions for Unit 1 or Unit 5. I just never had time to make any of them up. But these three, the last three I do. So there's a whole bunch of them too. So you can use those to practice for the exam. So you do have actually a little extra time in this unit between now and the exam to actually go through them. Okay. So I'm glad you liked the questions. So next time what I'll do is after class answer questions you may have in the homework. And of course tomorrow night too. Okay? So we will see you, you're welcome. We will see you on Thursday morning.